What we want to do is we want to develop the language that we need to analyze the error in Euler's method. Like in particular, what we really want to do is, say if we know the size of the global error here, say we want to reduce that by 90%, the question becomes, how much smaller do I need to make the step size to decrease that by a factor of 0.9? This is kind of what we're looking at, okay? And what we need is this big old notation idea. Okay, so if your bank balance was 1 million euros, 2,000 euros, or 1,002,098 euros and 21 cents, how much money would you say you had in the bank? You just say you'd have a million. So you've got the order of a million. Now that's not really a great example now that I think about it. But say even if you said, if you had this amount, you would say that this is of the order of a million. In a rough example is that anything that's kind of between 0.1 to 10 times something is of the order of it, but actually it's going to be made mathematically more precise. So the time taken to brush your teeth is of the order of 1 minute. It's a multiple between 0.1 and 10 minutes. The width of a pencil is of order of 1 centimeter. And when you order takeaway, delivery time is of the order of 10 minutes. It's going to be a multiple of 10 minutes, hopefully. And the pint man can put away the order of 10 pints in a single sitting. So, sorry, I'm trying to be cool and I'm not. Okay, so consider an infinite recurring decimal such as 1/3. Now, if you try and write this in decimal form, you get 0.3333, and I think I can just do dot, 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 and that goes on forever and ever and ever. Now, you can write this in a slightly different way, where this, of course, is 3/10 plus 3, this thing is hundredths, plus 3 1,000ths, plus dot, dot, dot. Okay, and this is actually something we're going to see quite soon, is the idea that you can add up infinitely many small things and get something finite. Okay, but what you need is that the things that you're adding on get smaller and smaller and smaller. Well, that's at a minimum. Now you can say stuff like this. You can say that 1/3 is of order 3/10. So a third is kind of a small multiple of 3/10, something slightly bigger than 1. 10 over 3 or something, I don't know, whatever it is. 10 over 9. So let's just maybe just write that there. So 1/3 is equal to 10 over 9 times 3/10. I think that's correct. Yeah. So it's a small multiple of 3/10. So that's how you can say 1/3 is of order 3/10. You can write stuff like 1/3 is 3/10 plus terms of order 3 over 100. So I'm not quite so sure how that would work, but like this, but you get 3/10 and then this stuff is some multiple of 3 over 100. Or you could reduce it even further and say that 1/3 is equal to 3/10 plus terms of order 1 over 100. So something like 3/10 plus some multiple. The problem is I'm not sure what the multiple is. Is it even, maybe it's 10 over 9. I'm not sure. Look, I'll just write it, wing it. Over 3, I think it is. That's just completely wrong. It doesn't matter anyway. The point is, the really important point is that it's some multiple of 1 over 100. And that's the idea. Okay. All of the terms beyond 3/10 are individually less than 3 over 100, like 3 over 1,000 is smaller. However, now there could be an issue where if there's enough of them, they could kind of add up to be a lot more than 3 over 100. But you can be a bit more precise. Here's the proper one. The number I was looking for was 10/3. So you can show that the difference between a third and 3/10 is this number, which is 3 over 100 plus 3 over 1,000, so on and so ever. And I think this is possibly even equal to I should be careful. So this would be, oh, this is the difference between them. 1/30. Look, it doesn't really matter. The important thing is, look, it's less than a multiple of. That's the important thing. You can make this precise, but I'm kind of missing the point. Okay. So what this means is, in this kind of a situation, you can say 1/3 is 3/10 plus terms of the order of 1/100. And then, like these terms, the important thing is actually that it's actually 3/10 plus some small or some multiple of 3/100. And this is way smaller than this. So what you can do is, if you've got a situation like this, and this is actually how we'll also write it. So it's 3/10 plus terms of the order of 1/100. And if this thing is way smaller than this, if you throw away these extra terms, which are small in comparison to this, you get an approximation. So that's a sense that a third is approximately 3/10, because the difference between them is only a multiple of 1/100. Yeah. A slightly more sophisticated use would be not to worry about the constant being between 0.1 and 10, and just say that x is of order y if x is less than a multiple of y. So for example, the area of a circle is of order r squared. So we say that the area of a circle is of order r squared. And this is where the important bit is, will come into it. So for example, here we'll say that the kinetic energy, which is actually a function of two variables, is certainly of order v squared. Here we get that the volume of a sphere is of order r cubed, and a pendulum, the period, is of order square root of L. Now this basic understanding of the variables gives you very qualitative information about the variables. So for example, with the area of a circle, because it's order r squared, if you double the radius, what will happen to the area? This is going to happen down below as well, but I'll just go over it now. So if you change from a multiple of r squared to a multiple of 2r squared, and what's 2r squared is 4r squared. So that means that if you double the radius, in terms of area, you get 4 times as much. And this means that you get kind of interesting things here. A 20, now forgetting about the crust, a 20-inch pizza, which a lot of us think that we could eat, is pretty much the same as 4 10-inch pizzas. And I don't know, could I eat 4 10-inch pizzas, but I definitely think I could eat a 20-inch pizza. Anyway, the one on the volume of a sphere is interesting, and it's about, and there's loads of things you can talk about here, but there's interesting stuff like why don't you see a 100-foot animal, 100-foot high animal? And the reason is, as you keep getting bigger and bigger, so say whatever, I'm not 6 foot, let's say I'm 5 foot, and say if I multiply my height by 20, my volume will go up by 20 cubed, which is something like 8,000. Okay, so if I multiply radius, what happens to volume? Volume goes multiplied by 8,000. But if you think about area, only goes as the square. So your area would only go by 400. Now think about this. So imagine me, I'm 100 foot tall. I'm 8,000 times as big in volume. So I'm 8,000 times heavier. But what about the strength of my legs? The strength of your leg is related to the cross-sectional area. But the cross-sectional area of my legs is only increased by 400 times. So you can't have a 100-foot human of the same proportions, because the strength of their thing, which is the area, does not grow in the same proportion. Okay, it's also related to, if you're buying diamonds, 1 carat, 2 carat. If you look at a 1 carat, 2 carat, there's no doubt a 2 carat is larger, but it's not twice as big in every direction. It's just it's twice as heavy. It's approximately 1.3 whatever it is, cube root of 2 times bigger in each direction. Okay, So what we've been saying here is knowing the order of a quantity allows us to understand roughly what's going on. So we know that doubling the radius of a circle increases the area by a factor of 4. So what I want to write here is something like this. Suppose you have an original radius, which we just call R0. Then the original area is pi. And the point is we don't need the pi to, we can just reduce it down to being order squared, but we'll show here. So the original area is pi R0 squared. Now let us look at a new radius, which is twice the old radius. Then what happens to the area? The new area is equal to pi times the new radius squared. And when you square 2r squared, you get 4 pi r0 squared. And pi r0 squared is the original area. So you get 4 times the original area. So doubling the radius multiplies the radius by 4. So here's another one. This is the one I was talking about. So doubling the dimensions of the diamond. So suppose the original, now that's a kind of say it's a perfectly round diamond. The original radius, gives a original volume of, now here again, like the 4/3 pi r squared doesn't actually matter. It's just a constant time. So I'm actually just going to write k. And the k doesn't change with the radius. So I get k r0 cubed. And then what about if I double the radius, which is the same as going from r0 to 2r0, or 1 character to, double the radius. Then what happens to the volume? The volume goes to k times the new radius, which is twice r0 cubed, and 2r0 by 2r0 by 2r0 is 8r0 squared. So you get 8k r0 cubed, and k r0 cubed is the original volume, but it's multiplied by 8. So doubling the side length, for example, of a cube increases the volume by a factor of 8. So this is why this is kind of important. Now here's the real technical definition, because what's happening is we're going to have, So we say a function f of x is of order g of x. So you say f is in order g, or f is equal to order g, if f is less than a multiple of fixed constant times g of x. Roughly f is less than a multiple of g. Now we're nearly writing the whole time that actually f of x, the absolute value of it, is equal to a multiple, but really it should be less than or equal to. Okay, so that's some of the language we need to do the error analysis for Euler's method. Okay, now we need to do something else. So how does a calculator work? So this is something I said earlier. Like, so if you were in Marina's class and you find that the solution of a differential equation, for argument's sake, is y of x equal to sine of x, or y of t equal to sine of t, funnily enough, you need to, how do you get like sine of 1? You need to use numerical methods. And so we're just going to give you like how do they actually do that, except we'll do log. So the question is, how does a calculator actually work? So addition and multiplication are easy to program. I mean, you know how to do long multiplication and addition. But how about finding the log of 2? No calculator can calculate log of 2 exactly, because it's infinite decimal expansion. It's about 1.609 or something like that, but it keeps on going. So calculators must use approximation. So we'll look at some ways that maybe they do it. Okay. So here we got a graph of y equal to log of x. Now they're smooth, which means that near a point that we know about, which would be this one, x equal to 1, y equal to 0. If we zoom in, and we can't zoom in really as much as I want, but if we zoom in, they look like lines. And that line, of course, is what we call the tangent line, and it's the thing I can't draw. Right, so they have good line approximations. Okay, so you probably have a fair idea how we'll do approximate log of 2 is, so we're trying to find this number here. So the x coordinate is 2, the y-coordinate is log of 2. And what we're going to do is we'll approximate this using the tangent. Look, it's not a great approximation, but we can improve it in various different ways. Okay, so I draw the tangent to the curve of x equals 1. To get the equation of the tangent to the curve, we need a point and a slope. We have a point, so all we need is slope. So how do you get the slope of the tangent of y to log of x? Well, the slope is the derivative. So if we want the slope, we're going to have to calculate the derivative of log of x. Do you know the derivative of log of x? It is 1 over x. And therefore, the slope of this line is the derivative evaluated at x equal to 1, because that's the point we're interested in. So I plug in x equal to 1 into this, I get 1 over 1, which is equal to 1. So I have a point and a slope. I can do the equation of the line. So I get the equation of the tangent line, this green thing, I may as well write it in green, sure. So I get y minus y1, the y1 is 0, equal to m, which is 1, times x minus x1, and the x1 is the 1 there. So therefore, the equation of the tangent is y equal to, now 0 doesn't do anything, 1 by x minus 1 is x minus 1. So we know points near x equal to 1, this picture is so bad, I'm so sorry, log of x is approximately x minus 1. So what do we got? So log of x is approximately x minus 1 for x close to 1. And we'll do an example with the calculator. So if I do, say, log of, we'll stop there, log of, say, 1.01. So I'm going to use the calculator for that. Now the calculator will just assume the calculator knows what it's doing. And I get 0.00, it starts 995. And I'll leave it at that. And that is approximately 1.01, which is the x minus 1. So you can see this approximation. So log of 1.01. So basically when x is close to 1, log of x is approximately x minus 1. So now the problem is it's not a very good approximation for log of 2. So if I go back and do that up here, so the tangent says, according to the tangent, log of 2 should be approximately x minus 1, in this case 2 minus 1. But in fact, using the calculator, log of 2 is approximately 0.693. So that is a fairly crap approximation. This error is of the order of 0.3. Now we actually should stop and actually say something here because it is important. Okay, there's two things. The first is, could we pick a value of x closer to 2 that we know about? And the problem is we don't really know too much about, the only other one we possibly could use is maybe e. So it could use e, because log of e is equal to 1. And then you could work with the point x equal to e, y equal to 1. And you can work backwards from 2, like e is approximately 2.871. But again, like how do you get the e? There's another approximation there. So you got to kind of catch 22 there. Now, the other thing I was going to say, something that's very important as far as I'm concerned here, is approximating percentage errors. It's something I'm going to ask you to do a couple of times. So if you want to define the percentage error in a calculation, it must be the error in the calculation. I'm writing Q for the calculation. So the error in the calculation, the error in the approximation is, and this is in the sense of percentage error, it's the error over the true value. not over the approximation. So for example, for the approximation of log of 2 using the tangent line, the difference between these is, I'll use the calculator for this. So the difference between 1 and log 2 is, I'll even turn this into an approximately. I'll just use 4 significant figures, 3069. And I don't divide it by the approximation, I divide it by the true value, which again, I'll use 4 significant figures, 0.6931. So I get approximately 3069 divided by 0.6931 to maybe the nearest whole percentage I get is about 44%. If you use the approximate value, you'll get a smaller error, but you should use the true value. Because if you multiply this out, you want to get that the error is a percentage of the true value, not the error is a percentage of the approximate value. There's a difference there between profit margin and profit markup. Okay, well anyway, we've got a crap approximation to log of 2 is where we are. We want to do much better. So what we can do is, rather than just using a line, a tangent line, how about we use a tangent parabola? So I think we're going to do that here. So instead of fitting a line to the curve, you could fit a quadratic or more complicated polynomial. So that's just sums of powers of x. And all are somewhat easy for a calculator, just combinations of addition and subtraction and multiplication. So the question is, could we write, say, using a cubic log of x, it's approximately some constant, which is probably the -1 from above, plus some constant times x, which is probably the 1 from above. So you get the a0 is -1 and the a1 is just 1. And then maybe add in an x squared to give it a bit of curve, and maybe add in an x cubed to give it some curve. And the question is, how do you find these values of a2 and a3? You can do it and we'll look at it. Now, how about maybe we have, so we'll call this thing, say, p3 of x. So this is the degree tree. The degree just means the highest power of x here. So could we go degree 4, degree 5, degree 6? So basically we just add more and more terms on. These are like more and more chances for the curve to really work, such that the Pn of x, so these polynomial approximations, get closer and closer to log of x as the number of terms goes to infinity. The question is, can we do this? So can we approximate something like a log of x with an infinite sum? And it turns out that you can. Now there's a lot of theory in the background here, and if you're doing a pure maths degree, you'll spend a lot of time on this. We won't spend loads of time, we'll just kind of tell you it's true. So the first clue that it might be possible to have something kind of finite equal to an infinite sum, apart from the 1/3 we saw, because remember, a third is equal to an infinite sum, is the following fact, that if the absolute value of x is less than 1, so if x is strictly between -1 and 1, you have that 1 over 1 minus x is equal to, in a certain sense, 1 plus x squared plus x cubed plus x to the 4, and you keep on going. Now the particular meaning of the infinite sum is, if you want to find the meaning of this infinite sum, it's a number such that if you want to get, say, within a billion decimal points of it, correct to a billion decimal points, you can if you add on enough of these. Okay, so you can get as close as you want to take enough. And of course here I'm saying, well, what is, say, the value? This is 0.5, you put in x equal to this. So the difference between these gets smaller and smaller and smaller the more terms you add on. So what you say is that the infinite sum is equal to this. Okay. Now if you're worrying about, a finite number of things, or a finite number being equal to an infinite sum, just think back of the 1/3. 1/3 is equal to 3 tenths plus 3 hundredths plus 3 thousandths plus 3 10,000ths plus 3 100,000ths plus 3 1 millions plus 3, 10 millions plus 3, 100 millions plus 3, billions, and you keep on going. The thing I'm adding up there's infinitely many things, and they add up to something finite. So there's nothing unusual about it. So for an example here, using only five terms, 1 over, so this is like your 1 over x, 1 minus x, is equal to an infinite sum. What you can do is, if you just put in 5 terms, you get an approximation. So 1 over 1 minus x is approximately equal to 1 plus x squared plus x cubed plus x to the 4 plus x to the 5. So you're getting an approximation like this. And so, for example, at point 2, look at the difference between them, it's tiny. So such infinite sums are called power series. So a power series, if you want to write it down, is a constant plus a constant times x plus a constant times x squared plus ... just keep on going. Now they don't make sense for all values of x, just some of them. Okay. So for example, this one, the 1 over 1 minus x one, only works when when x is between -1 and 1 and not equal to 1, certainly. I'm not so sure about -1. No, not equal to -1 either. Because what happens is, if you put in 1 here on the right, you get something infinite, which makes a bit of sense, division by 0. But if you put in a -1 here, this gives you a half. But this alternates if you put in a -1. So this is 1, and then you'll put in a 0, 1, 0, 1. So it does, the thing on the right doesn't get close to something. Okay. So above we used a line near x equal 1 to approximate log of x. The reason we used x equal 1 was because we knew all about the function at that point. We knew its value, log of 1 was 0, and its slope was 1 as well. As a rule, we also tend to know all about functions near x equals 0, and the Maclaurin series makes use of this. So given a function y to fx, the first thing we do is assume that is analytic. Now, what it means for a function to be analytic is that it's equal to a power series near a point. So you're going to assume for some function, I think we'll do it with sine of x, just as an example. So example, sine of x. So assume that you can write sine of x, sorry, this isn't approximately, this is equals a constant plus a constant times x plus a constant times x squared plus a constant times x cubed. And now I'm going to do something. The rest of the terms are a multiple of x to the 4, or less than or equal to multiple less than a multiple of x to the 4. Okay. So what we want to do is, for sine of x, is find these constants. So the way you do it is, the first thing you do is you say, okay, what's happening at x equals 0? So if you put in x equals 0 on both sides, you get sine of 0 equal to a0 plus, now what's a1 times 0 is 0, plus a2 times 0 squared is 0, plus a3 times 0 cubed is 0. And now this is where the order notation is useful. These are all a multiple of 0 to the 4, all a multiple less than a multiple of 0 to the 4, less than a multiple of 0, they all are 0. And sine of 0 is something that we know. So we found that a0 is actually equal to 0. Now just to kind of make this more general for later on, suppose this was f of x. And if I do that, a0 is equal to the value of the function at 0, in this case sine of 0, which is 0. Okay, now if you want to find a1, what you can do is you can differentiate both sides of this. So now to justify that is a bit tricky, but we won't worry about that. So we differentiate sine of x, we get cos of x equal to the derivative of a constant a0 is 0 plus fix the constant a1, and what's the derivative of x with respect to x is 1, plus fix the constant a2. Now what's the derivative of x squared? It's 2x. Fix the constant a3. What's the derivative of x cubed? 3x squared. And now I'm just going to write, we have terms of order. If I differentiate a term with x to the 4 or higher, it'll be a multiple of x cubed. Handy. And now what I'm going to do is I'm going to substitute in x equal to 0 into both of these. So if I do that, I get cos of 0 is equal to, now that's 0, I get a1 times 1, which is just a1, a2 times 2 times 0, 0, a3 times 3 times 0 squared, that's 0, and then multiples of 0 cubed, I just get zeros. And so I find that a1 is cos of 0, and cos of 0 is equal to 1. So we end up with the second term, the second constant, which is a1, is the value of the derivative at 0. In this case, 1. And you repeat the trick. So take this and differentiate both sides. So you differentiate cos of x, you get minus sine of x. The derivative of a1 times 1 is 0. Fix 2a2, and the derivative of x is 1. Fix 3a3, and the derivative of x squared is 2x. And then when you differentiate things that are less than a multiple of x cubed, they all come out to be multiples of x squared. Substitute in to both sides of this, x equal to 0, and you will get minus sine of 0 is equal to, so you get the 2a2, at x equal to 0, this is 0, and these are all less than a multiple of 0 squared. They're all less than a multiple of 0. They're all 0 as well. So just plus 0, those are zeros. And so what we get is, multiply both sides by 2, we find that a2 is equal to the second derivative, evaluated at 0, divided by 2, which in this case is minus sine of 0 over 2, minus sine of 0, 0, 0 over 2 is 0. Okay, and you go once more and you get this thing, and what you can show is that all of the coefficients are equal to an is the nth derivative of the function evaluated at 0 divided by n factorial. And what that means is, for example, with the example that we're kind of running with here, which is sine of x. Was it sine of x? Yeah. E.g., sine of x is approximately, now remember the first number was 0, so forget about that. Then the second one was 1, so a1 is 1 times x. So 1 times x, which is x. The next term is 0, and it's what's going to happen is it's going to go from sine to cos to sine to cos, and the sign is going to, the plus to minus is going to change as well. So if you look at it, if you analyze it and take your time, the next term is x cubed over 3 factorial, which is, I'll just write 3 factorial. Now, I presume you know what this factorial business means. So for example, 4 factorial means 4 by 3 by 2 by 1. Anyway, the next one is plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and that pattern just keeps on going forever and ever and ever. Now, if your x is small, these are all small. And so if your x is small, sorry, there's another little mistake here. If the sum goes on forever, it's equal. Now, what I'm trying to say here is that if x is small, these things are all quite small, and so when x is small, sine of x, so sine of x equal to x plus something small, so sine of x is approximately x. That's something that we would have spoken about with the pendulum. Okay. So you end up with this formula. If the function is analytic, now not all of them are, but sine of x is, cos of x is. We'll just give examples of just some analytic functions that I can think of off the top of my head. Sine of x, cos of x, they're both analytic. E to the x. Log of 1 plus x if the absolute value of x is less than 1. And then the other one, 1 over 1 minus x, if the absolute value of x is less than 1. So these are all things, these are all analytic. Then these things are equal to this in a certain sense. Now what you can do, so you got an infinite sum, and the idea, what happening is, you see you're dividing by this k factorial. If the derivative stays small, so let's just look at, this is an ak. So if the derivative stays small, so for example with sine and cos, the derivatives are just sines and cos's, and they're always just kind of between -1 and 1. So they stay small. But they're dividing by a factorial which gets big. And so if you have something small divided by big, these things get very, very small. So what happens is the terms further along get smaller and smaller and smaller. So you can just kind of chuck them out and you get an approximation. That's called a truncation. So you just take sum of the terms. Okay, so for example, if you take the first 4, you get this. Now, here, if you go back and do Maclaurin series for log of x, you get into trouble, because if you try and do log of 0, ask the calculator for that, you get undefined. So what you want to do with, say, log instead is either you change it to log of 1 plus x, that's fine. Or if you want to do log of x, you don't work with 0, you work with 1. So it turns out, you can do similar analysis, that if the function isn't analytic near 0 but near another point, then you can say that if you want to write f of x equal to some constant plus some constant times x plus some constant times x squared. In fact, I'm doing this wrong. Like this. That the constants are very similar, it's just you evaluate them a rather than at 0. So for example, log of x, that's how you do it. Okay. So there's just a relationship between these. So Maclaurin means, so here we just say Maclaurin is just this formula basically around x equal a. So in the next lecture, what we're going to do is we're going to use some of those ideas to analyze the error in Euler's method.